So people I know are excited about to hear the ongoing journey of my internet, and the internet installer came onto my property today and told me that they're ready to go probably in the next, he said 2 weeks for sure we'll have gigabit internet into your house. So you're on notice, Elon Musk.
So why does it sound like Cable Guy?
Now, is it my connection problem or have I gone offline? Oh, no. Okay. I complain about my internet and you can't find out because my internet doesn't work. That's ironic. Can you hear me now? Okay. All right.
Yes.
Okay. Good. Good. I don't
For
know
what it's worth,
anymore.
our Starlink started looking for different satellites last night.
That's always reassuring.
Yeah, it was just Dishy was just kind of pointing in all kinds of directions.
Yeah. Are you getting like a delay from me?
Say
Am I
something?
unsynced?
Yes.
Yeah, you are, aren't you? I'm gonna leave and come back.
Now we can talk about him.
Quick, boss is away. Hi, Sophia, by the way. Hello.
Hello.
Oh, he's back. Darn.
Quick, look busy.
That's nasty.
Yeah, close those games on your screen.
Yeah. Oh, why is my internet bad?
Well, I see Sophia moving around.
You had things to say about Starlink, I guess. So
between all green and all red, now all green. What? Okay, but now I'm back. Okay, all right. Okay. All right. Yeah. All right, it was Elon Musk heard my prayer and solved the problem for me. Yeah, but you're on notice, Musk. 2 weeks. 2 weeks. and then I get fiber optics. Okay. Let me think. Was there any other interesting story? So did you see that Edward Stone, the Voyager project scientist, retired today? 50 years of being the project scientist for the Voyager spacecraft.
Yeah.
That's amazing.
I can't remember how many times I interviewed him. He's good.
Yeah. But to just like also let that be a lesson to many of the scientists who have missions that are going to the outer solar system. Like, this is going to be your life.
Yeah.
Right. Whoever the principal investigator for the Solar Gravitational Lens mission is, or the Interstellar Probe, has just got to be prepared for the fact that they've just finished grad school and they will retire before their spacecraft is done its work. Which is kind of amazing. All right. I should get the chat up.
For what it's worth, Ed Stone was a basketball player in college.
Oh, really?
Yeah.
Okay.
Apparently a pretty good one, too.
All right. And then I've got the chat. Okay. All right. Let's get started then. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, October 26th, 2022. I'm Fraser Kane, the publisher of Universe Today. This week, we're going to be talking about a marshmallow world. ancient data finding Uranus rings, why NASA is trying to crash on Mars on purpose, and a star has destroyed the atmosphere of one of its planets. Joining me this week, we've got Beth Johnson. Hey, Beth.
Hello, Fraser.
Are you recovered from a busy weekend?
I think I've finally caught up on sleep. Yes.
Yeah. Others haven't, but that's good. And we've got Carolyn Collins-Peterson. Hey, Carolyn.
Hey there, Fraser. How's it going?
Good.
I spent time on the weekend with Pam and Beth as well.
As did I. Yeah. All right. Congratulations on the award. Tell us what you won.
Oh, well, as you know, Mark and I have been involved in Full Dome film production for a number of years, and I went out to a film festival for Full Dome out in Costa Mesa, California, earlier about 3 weeks ago. And at the end of it, during the awards ceremony for all the films, they awarded Mark and me a Lifetime Achievement Award for all the work we've done with Full Dome films and promoting Full Dome content. Total surprise to me.
Yeah.
I had no idea it was coming.
I would, and we were talking about this before, I would reject a Lifetime Achievement Award because, award received, life over.
Yeah.
Yeah.
I'm not done. I'm not done.
I'm not finished.
Don't put me on the shelf yet.
I'm not dead yet.
Yeah.
Yeah. Not dead yet.
All right. Before we get into this week's news, I want to give a huge shout out to our good friends at the Weekly Space Hangout crew. They're our friends, our fans, our executive producers. They call the shots. We do what they say. And if you want that kind of ultimate executive cosmic power, go to wshcrew.space and they will give you everything you need to just call all the shots. All right. Joining us this week, we've got our special guest, Dr. Sofia Sheikh. Dr. Sheikh, welcome to the Weekly Space Hangout.
Thank you so much. I'm excited to be here.
I'm super stoked to talk to you. I reached out to you a couple of months ago to see if I could interview you, and you were like, can't, busy, please. but I think you've got a little more time, which is terrific. So for people who don't know, who are you? What do you do?
My name's Dr. Sofia Sheikh, and I'm a radio astronomer right now working at the Allen Telescope Array with the SETI Institute. And I do a lot of things with that telescope, but my primary research interest is the search for extraterrestrial intelligence, or SETI, also known as the search for radio technosignatures, to use the new hip language.
Oh, I didn't know that's the new moniker for it is radio techno, because there are now so many. Like, you can't just say SETI. I mean, are you looking for chlorofluorocarbons? Are you looking for the nighttime radiation are you looking for evidence of a global thermonuclear war? So I guess, what is the state of SETI right now? How many technosignature radio searches are being done today?
Ooh, that's kind of a tricky question, honestly. Because now, compared to 20, 30 years ago, there are so many cool new radio facilities that have come online. Chime, Meerkat, the ATA, which I work on, kind of goes on and offline, and that's a whole story in itself. But the real goal is to move towards commensal searches. And this is the idea that, you have scientists who propose for time and they say, I want to look at a pulsar or a quasar or the interstellar medium, like pick your object. And in the meantime, that data goes, to that science operator, but also some of it goes into a SETI search backend so that we can be doing searches simultaneously all the time while other people do other radio astronomy. So trying to count them is kind of hard, but that's what we're moving towards in the field right now.
And fairly recently, you at the SETI Institute were able to negotiate these agreements with different radio telescopes to get access to this pipeline of data.
Yes, it's a pretty recent development, but the kind of impact on the field is huge.
But I guess, how is it different? Like, if you're like tasking the telescope to various objects that are interesting to you, how is that different from you sweeping through data that has already been gathered for some other scientific purpose?
There definitely are differences. And so one thing is like the objects that we're interested in for SETI are more similar to what astrobiologists generally are interested in, right? We like exoplanets, we like nearby stars, we like sun-like stars. And often those are the targets that don't really emit radio waves
Right.
naturally. So our target list might look a little different. So for instruments where we do have full control of where the telescope's pointing, like the ATA, then we can prioritize those sorts of targets. And then for the commensal searches, we kind of have to piggyback on whatever anyone else is interested in looking at that day.
But there have been some pretty interesting surveys. I know there was the one done with the Murchison Wide Field Array in Australia, where they were able to do a very significant SETI search at the same time that other research was being done. You were involved in that, weren't you?
I was not, but I'm
Okay.
aware of it.
But I know people on the team with you were. Yeah. So, I mean, is that like the ideal that you've got these? Because I mean, the telescopes are getting so much better. Like when the square kilometer array comes online, that's just got to be the perfect machine for this.
It'll be fantastic. So yeah, I think it's good to have a mix where we can have a lot of data coming in all the time from these like commensal piggybacking searches, and then also be able to kind of follow up on new ideas about, oh, maybe technological life in the galaxy will be at the galactic center, or maybe it'll be at some particular target that did something weird recently. And having that power to follow up and execute our own searches in weird and new ways is also really important.
It really feels like SETI and other searches for extraterrestrial intelligence is gaining a lot more scientific recognition, acceptance, approval at this point. I know NASA has hosted you to sort of work out how technological searches might work. How do you think the field has changed over the last few years?
So with the caveat that I've been in the field for much shorter of a time than a lot of my coworkers.
But you've heard their stories, their sad, sad stories, right?
Absolutely.
Okay.
5 or 6 years ago, the Allen Telescope Array just wasn't doing much. It was mostly just sitting in a field, and it looks nice sitting in the field there if you can see that image. But it definitely was a very difficult time for the field, kind of through the 90s and early 2000s. And we are seeing more of an influx of interest and funding, and I think a recognition that technosignatures and biosignatures, like we're kind of working toward the same goal, but with slightly different assumptions. And given that we don't know what's out there, it's probably good to have a lot of people working under a lot of different assumptions and just see what we find. So I think that attitude is becoming more prevalent, and that's kind of where I stand as well. So it's nice to see that becoming more popularized.
I mean, like for the longest time, I think a lot of scientists didn't consider the search for aliens to be science. Do you think that the thinking has come around on that, or do you think there's still a lot of people that don't see that as science?
Definitely depends who you talk to. I've encountered both views in my career, and honestly, I see a lot more of the friction between kind of more traditional astrobiology, if you want to call it that, searches for biosignatures from microbes in exoplanet atmospheres, in the solar system, in situ, things like that. And I think it's just a reorganization sort of what we think the search for life should include and what it doesn't include, and how our understanding of like the prevalence of exoplanets in our galaxy informs those positions. So I would say most people agree that it's science, and then the question gets down to the nitpicky details of like, okay, how important is this science versus my science or that other science? And that's always going to be difficult.
But there's really, there's some interesting papers. I feel like you worked on this one. Maybe I'm wrong. Jason Wright for sure. But just this idea that it's probably more likely that we will detect technosignatures before we detect biosignatures.
Yeah, I was involved in that one.
Yeah, I felt like you were. Yeah. So can you explain why you think that's the case?
It's the argument that the paper makes is mostly that technosignatures could be more easily detectable, and so we just don't know. And I think a lot of people assume, like, okay, you have to start with your planet with no life on it, and then there's some gradient, and then your planet has simple life, if you want to call it that, like bacterial or viral or something like that. And then you go from there, and some of those planets become technological with a species like humans. Uh, and so, in that logic, it seems like there should be many more bacterial planets for every planet that develops technology. But the cool thing about technology is once you have it, you can start moving around. And that's a big part of the argument is even within the solar system, we've left technology that we've created on planetary bodies, on asteroids, free floating in space, beyond the boundaries of our solar system if we want to talk about Voyager. And so even if you only have a couple planets that develop technology, maybe the species that do that can then spread beyond into the galaxy in a way that's really hard for microbes, even if you count things like panspermia. The math gets kind of tricky if you want to leave your own stellar system. So that's one aspect to it. Another aspect is that for effects, say, on an atmosphere from a bacterium producing oxygen or something like that, the bacteria need to be around to have that effect. And if they're not around, then abiotic processes often will take over and remove that biosignature over time. Whereas you can think of technosignatures like maybe Dyson spheres built around a star or other artifacts like that that could last way longer than whatever creates them. And so that's another aspect to the argument is maybe technosignatures will stick around longer than biosignatures. And then I guess there are kind of three main points, so I'll hit all three.
Yeah,
The third one is just detectability. If we want to send a message across the galaxy, we can. But even if a bacteria wanted to, you're kind of limited by your capabilities. And so just finding something that's more detectable and more unambiguously created by life and not just astronomy as it plays out in the galaxy is the other benefit.
I mean, as we're here in the year 2022, a lot of the technology that you're working with is brand new. And yet we are, we have space telescopes, we have Earth-based observatories. Our ability to perceive the universe and ideally biosignatures, like maybe right now it's right at the very edge of what we can perceive, but in 100 years, we will have an exquisite vision of the universe out to thousands of light years around us and know with almost certainty whether or not there's life on different worlds and so on. Do you think about the other way around, that the aliens are out there and are certain of our existence?
That's always kind of a tricky question to answer because it depends what's our observable signature that we've left on the Earth and how does that propagate through space and therefore time.
Mm-hmm.
And it's the time axis that gets a little tricky because a lot of the biggest impacts that humans have had on the surface of the Earth, things that people will kind of group together and call like the Anthropocene, are impacts that have only happened over the last 100 years. So things like industrial pollution of the atmosphere or radio signals being generated and sent off the surface of the Earth. So within 100 light year radius, maybe we are known about. But beyond that, you kind of have to wait for the information about our technological presence on our planet to spread throughout the galaxy. So there are some competing timescales involved.
Right. However long we've been sending out radio signals, but it does feel, I don't know, like people always say to me like, oh, we shouldn't try to send messages out to space, but I feel like we have already, and just by existing. And when you think about the kinds of signal, the technosignatures that you're looking for, a lot of those are the stuff that humans are doing to our planet. It feels hard to hide.
Yeah, there are a couple of fun papers about how you would hide if you wanted to.
Yeah.
But for the most part, a lot of the things that we're doing, like the technosignatures we're generating, we generate kind of in the natural course of doing, kind of being the civilization that we are and doing what we do, and for better or for worse. And even the radio signals kind of fall under that. And one of my favorite examples is that Arecibo's like strongest radar pulses that it used to send out were often used for radar imaging of asteroids, near Earth asteroids, to try to keep an eye on where stuff was for planetary defense and make sure that there aren't any killer asteroids on their way in. And for us, that's sort of like, it's very loud, right? If anyone was looking at the right time, they would totally see us, even from hundreds of light years away.
Mm-hmm.
Like, it's very noticeable, but also it's not really negotiable. We kind of have to do that. And maybe there's an argument to be made that any species in a solar system that has this sort of orbital environment might also be doing the same thing. So some signatures
Yeah.
you can hide or not do, and others you kind of have to.
Yeah, and I know the research. I think it was David Kipping was talking about sending out a laser to try and compensate for the transit as the Earth goes around the sun, and it seemed very difficult to pull that off. But a great idea. So what answer to the Fermi paradox do you find most believable?
The answer that we have not looked enough to be able to set good constraints on whether anything else is out there, which I know a lot of people find unsatisfying because they're like, SETI's been going on since the 60s, you've had half a century to work on this, and it's like, yes, but for decades those searches were accomplishing a millionth of what we can do now in a night. So I think we're kind of at the cusp for SETI searches of actually being able to make statements about, okay, we are sure that for this large swath of the galaxy, for these large swaths of frequency, that we don't see technological activity. And once we can say that, then the Fermi paradox gets more interesting. But the short answer is just that we haven't really looked through enough of parameter space to know what's out there at all.
What would it take to meet that level? If you thought about, I'm going to write you a blank check right now. What kind of setup would be the ideal machine for doing searches, you think?
I mean, the biggest thing is kind of what we talked about at the beginning. Like, you need more time on sky. Like, we liked saying ASAT, all sky, all the time. That's the goal.
Right.
If we can
Every
be sure,
star, every frequency, all the time.
and then you have to say, okay, what if they only send a message once every orbit of their planet, once every year, or once every 100 years? Like, you can't start setting limits on periodic transmitters until you have continuous coverage for a long time. And that's something we haven't started to do at all. I can tell you that, we looked for 42 hours in a reobservation we did of Proxima Centauri, but if they sent a signal once every year, we might not see it at all. So just getting those numbers to be larger, time on sky to be more consistent, and that's when we can really start hammering down what's actually out there.
A funny comment that I get on a lot of my videos, someone says you're not ready to learn the truth. Now they generally assume that we're hiding evidence of UFOs, and that's why, because we're not ready. Are you ready?
Depends
Ready
what the
to hear the signal?
technosignature is.
Yeah.
For radio signals, like we have our pipelines, we've had close calls, right, where we've seen things that looked kind of like an artificial signal, kind of like it was localized on the sky. And in the end, we've been able to prove that all of these things have been Earth-based interference, or they never occur again. And we can't scientifically prove one way or the other what was going on in that case.
Well, I more mean like emotionally ready, psychologically ready.
So in one of those cases, I did have a moment where I was like, what if this is the signal?
Yeah.
Capital T, capital S. And I think science and human emotions work on very different timescales. So I had like one evening where I was super excited, and then I was like, okay, I have to do like the groundwork now to see if this is real. And that took months. And
Oh, yeah.
plausibly, with things like we were talking about Venus and phosphine, right? Like follow up can take years. So it's hard because you have that reaction where you're like, this could be the signal, this could be the
Yeah.
evidence of life beyond Earth. But then you have to sit down and go back and do the work and collaborate with people and take re-observations. And I don't want to say it's hard to maintain excitement through that process because that sounds kind of negative, but it definitely tempers it, where it's like, all right, now we gotta prove it.
It's like a fire alarm going off in the office. You're like, oh, fine, gotta leave the office. It's not a fire this time, but except it would be good news. But anyway, the analogy is starting to fall apart. Sophia, what is the best place for people to follow the work that you're doing?
I think the SETI Institute website and the kind of news and press and blogs that they do are a really good place to keep up to date with the searches we're doing with the Allen Telescope Array. There's a really cool piece on there about a nearby star survey that we're doing right now. And also I would recommend, there are like a couple big groups that do this sort of work. So I'll shout out Breakthrough Listen, which I've been a part of for a long time. They're on all the socials and keep everyone up to date with kind of the newest results from that group as well.
I'm going to recommend Google Scholar. Search for Sophia's name. There's a lot of papers that she's worked on, and they're all very readable. And, if you're into this kind of thing, into this idea of the search for life beyond Earth, I think you'll find a lot of the ideas in there quite exciting. So thank you so much for joining us today. Good luck. If you do find aliens, will you let us know?
Absolutely.
Awesome. All right. Thanks a lot. Take care.
Thank you.
All right. Carolyn, can you hear us now?
Yes, I could only not hear Sophia. So I don't know what happened. I just got a big
Oh,
big
really?
thing
You
like
missed
this
it.
across her.
Wow.
Yeah.
We did
Not all of it.
complete
No, I
an
heard most of it.
entire interview. You can watch it later, maybe. All right. Let's get
Yeah.
on to, I want to talk about NASA crashing on Mars on purpose.
Yeah, well, I thought this was kind of an interesting story. But to give you a little background, of course, you realize we've been landing things on Mars the last few years, and we're packaging them up in bubble wrap, and we're trying to get them safely on the surface. But that's really expensive, like millions and millions and millions of dollars to get this to get these sky crane enabled things to get onto the surface. But it's enabled a lot of great science. But what if you want to go to places where maybe you don't want to land something with a sky crane or a bubble wrapped spacecraft? Why don't you just do it the old fashioned way and crash it into the surface? Now, we used to do that, and we didn't do it intentionally, of course, but we used to crash things into the surface. And you get these rapid unscheduled disassemblies, right? Like Elon likes to talk about. But if you could do it safely, you could actually get spacecraft to areas that we aren't really going to be sending sky crane enabled spacecraft to, like maybe Valles Marineris or Noctis Labyrinthus or someplace like that. So to do
Or just
this, a group of
anywhere.
astronomers,
Like if it works.
well, or just anywhere that isn't where we've already landed, right? So a group of technical folk at JPL engineers are experimenting with managed crash landings, and they're using an assembly called Shield 1, which stands for Simplified High Impact Energy Landing Device. And it's kind of the prototype equivalent of a crash bumper. So you'd see it here.
Right.
And what they want to do is slow down the spacecraft on the way in instead of doing this, 7 minutes of terror, with a sky crane and all that. You slow down the spacecraft coming into Mars using atmospheric drag, and then theoretically the crash bumper would keep the instrument safe, and then you could send your lander to whatever exotic place you want to go to. So in order to make this work, they started testing Shield in a drop tower at JPL, and they put in some instrumental, kind of like the equivalent of crash test dummies. I think there was a smartphone and some other electronics inside this thing, and they dropped it. They surrounded all of this by what they call a collapsible attenuator, and it's again like the crumple zone for a low speed crash bumper. Then they put it to the top of the tower, and then they basically let it go. And it crashed into a barrier at the bottom of the tower at about 177 kilometers per hour, which is about what you get if you slow something down using atmospheric drag during entry, descent, and landing. So the result of this first set of tests were that the onboard accelerometer measured this incredible impact, found that it had a force of about 1,000,000 newtons, which sounds horrible. I mean, it's like 112 tons of stuff smashing against a target. So
That's
you
too
think
many
nothing is
newtons.
going to survive, right? It sounds terrible, but it actually worked because yeah, they put this crash test bumper on there and it worked. So the electronics were still functioning. I guess maybe they used the phone to make a phone call or something. They did get some plastic pieces that broke off as part of the assembly, but it actually worked. And so now they're going to take the next steps to do some more testing, of course. So I don't think the next missions are going to, be surrounded by crash test bumpers, but it's something that they can think about for future missions. Smaller payloads, probably, that you can get into some more interesting places.
And so the plan here is that you would have, like, it would make the flight to Mars, it would use the
Mhm.
aeroshell, it would ditch the aeroshell, it would deploy a parachute, and then it would just ride the parachute down and crash into, or maybe ditch the parachute moments before landing, but it's coming down at
Yeah.
170 kilometers an hour, and then the crumple zones on this spacecraft just compact down
Mhm.
in an elegant
Yeah.
way so
Yeah.
that that final payload can survive the landing and then just get to work, deploy the rover, and away we go. It
Yeah.
really does feel like the
Yeah. I don't think
simple
there's any rover
final
that they're talking about, though.
evolution.
Yeah.
Right, but whatever it needs, but it really does
Mhm.
feel like this sort of final simple evolution of this. Like, the best landing system is no landing system.
Yeah. I mean, it worked really well earlier. It's just that we broke everything apart when we did it. But I think I didn't see anything where they were going to send rovers right away. But they certainly, I would think, want to use parachutes. You can certainly those aren't going to cost as much as everything else that they've been trying to do. But yeah, the parachute would help you. You're going to have some atmospheric drag, and then you get down, and maybe they can get that terminal velocity down a little bit, so that you're not
Yeah.
whapping it, making your spacecraft endure all those newtons of force,
Well, I mean, but
and
it
and
sounds like it's
hopefully and hope that
fine.
your electronics work.
Like
Yeah,
like
yeah.
the spin launch, they're hitting, like, when they're rolling up the spin launch, they're hitting 10,000 Gs,
Uh,
which seems sort of in the
yeah, yeah.
same kind of
So they've done a bunch of tests with
spectrum.
that too. Yeah,
Yeah, and so I think that there
yeah.
are there are limits to what this kind of technology can handle if you harden it and cushion it and then have it do this
Hmm.
crumple, these breakaway panels nicely. That seems like a really elegant way to send payloads to Mars. Colonists to Mars, maybe not. Maybe
Yeah,
not
and I
colonists.
was well, maybe not that, but yeah, spam in a can, right? No, I think
Yeah.
one of the things I was thinking was they probably I don't know exactly what the materials are made of, but they probably could get the weight of the material down and still have it be pretty bouncy, pretty crushable, and still be able to protect your interior experiments, whatever you're sending up.
Yeah. 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 Very cool. I really like that. All right, Beth, let's talk about the
Yeah.
Marshmallow Planet.
So the Marshmallow Planet is an exoplanet called TOI 3757b. It is orbiting very close into a red dwarf star, and its orbits about 3.5 days. And it has the density of a marshmallow, basically. So you take a Jupiter-sized gas giant and fill a bathtub with water that can fit that, and it will float, just like Saturn would. So it's like the least dense exoplanet we've found yet.
So I have two questions for you. How, and also why?
How is a really good question. There actually are some there. That's kind of the question, because one of the things about red dwarfs is that they are very active, and it's generally assumed that when you have a gas giant close into a red dwarf star, that all of the stellar explosions and stellar winds will blow that atmosphere off. And so instead, here we have is an atmosphere that's still there. It's just very thin, And one of the things that they think might be happening is that it's getting sort of puffed out from the heat. So it isn't a lot of atmosphere. It has mostly been blown away, but because it's getting so superheated, it's kind of puffing out a lot. And that's one of the thoughts as to how. As to why, I don't know. This is a fairly sort of new type of exoplanet that we found in the last few years. A friend of mine from undergrad, who's a grad student, is basically, she did her doctoral thesis on it, and so she's kind of one of the experts. And they've been referred to everything as cotton candy planets, puffy planets. Now we've got a marshmallow world. So there's definitely a very light, flavory theme going on here. But they are fairly recently discovered, and so every time they find one, they kind of add it to the list and go, "All right, we need James Webb. Where's James Webb? We've got to have the telescope." So
I mean, is this a James Webb kind of world? I
yeah,
wonder.
they're really wanting that. They really want to analyze the planet and find out, like, you know, what it's made out of exactly. Figure
Mhm.
out how much of the atmosphere is left and that kind of thing.
Now, is it like it's extremely close to its star, though, isn't it?
Yes, like I said, it orbits in 3.5 days. It's not far at all.
Right. Right. Now, 3.5 days, that is farther than the other planet we're going to talk about shortly. So maybe the one that Carolyn's going to be talking about is the next evolution of this process. But so I wonder how common worlds like this are, or are they a temporary? Like, is this in the process of turning into a Mercury?
That's another piece of the theory as to what happens. Like, we might be catching these in sort of that interim stage where we've gone from, say, like a super Earth mini Neptune that has suddenly had all of its atmosphere sort of superheated and puffed up, and it is in the process of actually getting stripped away,
Yeah.
as we're going. And then yes, we would be left with, say, like just that rocky planet, that inner core. But at least we have an atmosphere because we can see it.
Yeah, but I mean, like when you've got a star like a red dwarf star that is putting out a lot of these killer flares, they're very young. They're in the first billion-ish years of their life, and then they settle down. And at the same time, isn't it an interesting coincidence that you've got this marshmallow star around a feisty red dwarf? Could very well be that after they've fully matured, they've utterly destroyed the planets around them. It's very cool, but Marshmallow Planet. I don't know.
Yeah, the I think the total amount, it's 0.27 grams per cubic centimeter. That's the density of it. So it's like half that of Saturn.
Wow. Yeah, because I remember like in the books that I used to read as a kid, there's pictures of Saturn floating in the ocean and stuff.
Hmm.
Very cool. All right, Carolyn, let's take this one level up then, where the planet is orbiting even closer, and things did not go well for it.
No, it didn't, and it's not floating in a bathtub either. So, um, so this is a little planet. Well, it's actually not little. It's a super Earth that is orbiting around an M dwarf star. So M dwarf stars are actually pretty numerous in our galaxy. They're usually stars that are smaller than the sun. They can sometimes be as big as the sun, and they can also be very active. So they're sending out flares and all kinds of outbursts. So the question here is, what happens if you put a rocky Earth-type planet with an atmosphere fairly close to one? And it turns out it's not really a great thing for the planet, even if it's in the habitable zone or even closer. So astronomers were looking at one called JG 1252b, a planet around a star, and it's orbiting this M dwarf. And this thing's about 65 light years away from us, and it appears to be a fairly active M dwarf. The planet itself orbits the star about twice every 24 Earth hours, and it's also in a very tight elliptical orbit. I think it's about about 1.3 million kilometers away from its star. So it's actually fairly close, and the elliptical orbit brings it much closer to the star at some times than others. And that causes it to basically bake the surface. So think like Mercury. The surface is alternately baked and frozen. The outbursts have actually scoured away the atmosphere, so there does not appear to be any kind of atmosphere around this world. It's completely blown away. So this is what they found when they first looked at this thing with the Spitzer Space Telescope during some sort of an eclipse. So it's not exactly like Mercury, but what's happening to this is that there's absolutely no way that this planet's going to be a life-bearing planet if we're looking around for life-bearing planets. The other thing that when I was doing the reading on this thing, I was going back and they were looking at Mercury's totally been stripped of its atmosphere. It turns out that our sun is also pretty active, and we lose a little atmosphere every time it gets active. Now we get to regenerate our atmosphere with volcanism or whatever is going on. This planet doesn't get to have that.
Yeah, and so it's interesting, right? Like the one that Beth talked about, it was every 3 days around an M dwarf.
Yeah.
This is 12 hours around an M dwarf.
Yeah.
And so you can really see like that's too close to get to your star.
Yeah, and so the bummer here is that there are many of these M dwarfs in the galaxy for life on them, but if most of them are as active as this one is, then that reduces the number of, I guess, hospitable planets that you're going to be looking for. But it also means that there's still some out there that could be hospitable if those planets are, not being basically having their atmosphere stripped off, every so often.
It's really interesting. I mean, for the longest time, the assumption was no, these planets are not going to be hospitable. M dwarfs are, they can release flares that are hundreds of thousands, millions of times more powerful than anything the sun can release. And because they're cooler, the planets have to be, the habitable zone is snugged up tight around the star. And so not only are you having to be closer to your star, but the flares are brutal. And so no, there's no way that you can survive. And it'll be interesting. I think we're going to be able to get some pretty solid answers to this question now with Webb, with other telescopes out there that are going to be able to study the atmospheres of these planets and really say, okay, great. Any planet that is within the habitable zone of an M dwarf star is a goner. But maybe they'll be able to find examples where there aren't, right? There's a piece of research about that we saw a couple of weeks ago that astronomers had detected a planet through the radio emissions coming from its magnetosphere. And they didn't know the planet was there, but then they detected the burst of radio waves coming from the flare interacting with the magnetosphere. And it's like a twofer. You discover the planet, and you also discover that it has a magnetosphere, which is great. And so it'll, again, be interesting if you can bring those radio telescopes online, like the Square Kilometer Array. Now you're seeing the planet, you're seeing its atmosphere or lack of atmosphere. You're also seeing, as these flares wash over the planet, are you getting any kind of radio wave flash from the magnetosphere that's attempting to protect it? And I think we'll get this great understanding of what wrecks planets. Are these red dwarfs a write-off or not? And right now, I think all the astronomers are straddling the fence. And I see one paper that says they're goners, and I see one paper that says, well, maybe there's a chance.
Yeah, you do see that. And then there's also there's also a sort of an implication in the paper that I read that, well, maybe we ought to be looking at planets that are a little bit farther out from this, if there are any around these M dwarfs. What's going to happen with the ones that are 2 and 3 and 5 and 7 AU out. I don't think the chances look good. And that you bring up magnetic fields. I mean, there's just a whole area of magnetic field studies that we're really starting to see more of in terms of what's happening with evolution of different activities and processes in the galaxies. It's got to be the same with the planets as well and their interactions with their stars.
Yeah. I mean, it's really exciting that we're getting to this point in exoplanetary research where we know of thousands. There are 5,000. I've lost count. 5,000 plus known planets. 10,000 candidate planets. It wouldn't be unreasonable in the next 10, 20 years that we'll know of hundreds of thousands, millions of planets. And we will also have
Yeah.
characterized their atmospheres, detected their magnetic fields. We're going to know a lot about planets in all shapes and sizes and all forms. You've got the extremely large telescope that can do direct imaging. It's going to be a pretty great time to know. And just think, like, I remember when the first planet was discovered around a sun-like star back in what, 1995, and yet here we are having these, like,
Something like
we're
that, yeah.
talking about the atmospheres of just another of the thousands of planets that have been discovered. It's crazy to think. I love it.
And it's only 65 light years away. And I think Beth's was what, five or 600 light years away.
Yeah, that sounds right.
Yeah.
Yeah.
Okay.
Yeah. The other thing that blows me away is almost every story I've done lately is that the ending story in every press release is, well, it's going to be great when we can use JWST to look at it.
Yes.
It's like,
Yeah.
here we go.
That's like everything. It when we can use JWST, I'm like, okay.
Yeah, there's a line. Get in line.
There really is. Yeah, you gotta get behind the early science.
Yeah, get in
stuff,
line.
Yeah.
And then the line gets really long.
Have you looked? And we're digressing, but also we have a little extra time. But like, if you looked through the list, I love to go and look at the list for the week of what GWST is observing. So this week or last week, they were observing Fomalhaut, which is a star, but it's that Eye of Sauron star that is made famous by Hubble and other observatories. I can't even imagine what it's going to look like, and we have to wait a year for the images from this to be released, unless they take pity on us. Oh, was it Pluto this week?
Didn't they look at Pluto?
Oh, I don't know.
Well, it was within the last couple of weeks, I thought.
Okay, yeah, I haven't checked it like every day. And then there was like another galaxy that looked really cool.
They tweet about it.
Yeah, I was gonna say I follow a Twitter feed where it's basically, what is JWST looking at right now?
Oh, really? Okay,
Yeah.
I'll dig that up. Yeah, I'll dig up that Twitter feed. That sounds terrific.
Yeah, I don't always catch it, but when I do, I'm always like, oh, what have you got?
Yeah, and so if you then
really,
double check against the cycle 1 list of all of the targets that JWST is able to spot, you can see which ones are part of larger surveys and the data is released instantaneously, and which ones are part of the ones where the scientists get to crunch on the data for a year. And even though we've been able to report on a lot of amazing stories and a lot of incredible pictures, there is this avalanche coming that we're not going to feel for another 9 months. And then, we're 100 days in of public or of like actual scientific observations made by JWST. 265 days from now, all of that original stuff getting dumped onto the JWST archive, and then everybody gets to get their claws into it and start publishing pictures and seeing what stuff. And that's why I just did an interview. I'm going to be releasing this tomorrow with Judy Schmidt, Space Gek.
Yeah.
And she has just we need more Judys, because there's so many incredible pictures out there that people need to be looking into and processing. And she's just one lady. So
and I'm deeply appreciative of the early science release program. That has been really fun to get all of these results, even though they're not peer reviewed and everything, but to get them to be able to see these images very quickly has been amazing.
I mean, I think we've been able to report on like 2 or 3 stories a week on Universe Today. But when you look at the observing run, you're watching these, these really cool things show up, but then also you see the train going by of 12 amazing observations that happened in the last 4 days. You're just like, oh, please, can I see what you saw? Can I see those pictures? But I guess, I mean, they need to science them. There was that those rings, you know, that crazy Wolf-Rayet star with the weird rings.
with
That
the
Oh yeah,
like
yeah.
concentric
yeah, with us.
circles.
Yeah, and this is one of the ones that Judy accidentally found, and she published to her Twitter feed. She was like, "Does anybody know what this is?"
Mhm.
And we jumped on it immediately, and I'm like, "Okay, that's a story." And then we reached out to the researchers, and they were like, "Please don't talk about this yet. Like, we don't exactly know. We have some math to do." And you could see that they were just horrified that this data had gone out onto the internet without them getting a chance to even just try and figure out what it is that was going on. And so it took like an extra. We waited. Nobody else did. We waited until they were ready, and we had a great answer and we had a great story. But yeah, we had to wait like a month while everybody else had already moved on.
Just imagine what the fire hose of astronomy is going to be like in 6 months.
Yeah, exactly. As soon as that data starts popping out into the public archives, and but I mean, the scientists won't even take. They're not going to need the full year. They're going to need as long as they need, and I think the hope they also have a sense of urgency to get their research completed, get their papers out, get them published. So you've got on the one hand, you've got the deadline that is creeping up on them, where the vultures are ready to jump onto their data, and then on the other hand, you've got them being urgent on the other side. And so I think you're exactly right. You know, we're going to see these papers coming out over the next, say, 6 months, 3 months, and it'll feel like an avalanche. And a lot of people are saying, like, well, where's all the information from Webb? It's coming. Buckle
Maybe
up.
hopefully it'll make up for the sort of like summer quiet time we had when the lockdown really the effects of it were felt. You had like, here's a story.
Yeah. Yeah. Yeah, exactly.
Yeah.
All right. Close this off, Beth. Talk about finding Uranus's rings in old data.
Yeah, so this is kind of you never throw data away. NASA has been doing a very good job of trying to find ways to keep all of their data archival. They have their PDS, Planetary Data System Archives, and so someone decided that since there were Voyager look back images of the rings for Jupiter, Saturn, and Neptune, why not Uranus? And so, of course, the archive is publicly available. You can go and download data. And his name is Ian Reagan. He ran some of this data through image stacking software and discovered some rings that we'd seen before in the Keck telescope images, but he found them in these look back Voyager images. And so it's that innermost ring on the picture on the right. So you can kind of see just outside the crescent of Uranus, you can see this one ring, and it matches what it's called the Zeta ring. And so he's actually managed to find it in this data, and he posted. Again, it's like Judy. He posted it to Twitter and went, "Hey, I think I see the Zeta ring in this image." And someone else grabbed it, sent it to somebody at University of Idaho, and they went and looked at it and went, "Yeah, no, you're right." And they went to DPS and presented it. so here's this guy on Twitter going, "I just did some amateur processing and found this. Here you go."
And boom, research done. That's
exactly.
really cool.
Yeah. So it's thank you NASA for dating all of your data and finding ways to keep that publicly accessible.
I mean, I'm really excited, and when I did this interview with Judy, I was just so excited by the opportunity, this partnership that you have with people who are looking through the data and trying to make images that are aesthetically appealing, and yet at the same time they are studying them very carefully and noticing really interesting stuff. Judy explained the story where she saw what looks like rays, a shadow from a supermassive black hole, and they're doing follow-on observations to find out. It's believed that this is a quasar that is casting. It's got a ring of dust around it, and it's casting this shadow out into space from the illumination of the quasar being blocked by the ring of dust. And in her pictures, you could see this cone that is that is casting out into space. And she was like, is this real? Am I seeing this? And so she reached out to some scientists, and they're like, that might be a shadow from a quasar. And
I do actually remember that series of tweets, and I also love that she reaches right out to the science community and says, processing an image, I think I've got something weird, someone help me out here.
yeah. And so it's such a great partnership. It would be great to see more of that. Like, anyone who's watching this, listening to this data is out there. It's freely available. All you do is you just download a picture into your Photoshop or whatever you want and just start mucking around. And over time, you will become good at producing these kinds of images. And it helps with the outreach to the public. It helps other people appreciate the beauty and wonder of astronomy. And it can teach us a lot about the universe as well.
So I know Nancy will include the link to the Sky and Telescope article in the show notes. Check it out, because at the end of it, they actually have Ian's steps that he did for processing the photo, including like where he found it and like what it all was and the software that he used. And it was all free software. So if anybody else wants to do it, there are some steps out there that you can take to kind of get your feet wet and figure out how it works.
That's awesome. Very cool. All right. We've reached the end of our hour-ish. Beth, tell us, what are you working on and where can people find out more?
Right now, we are kind of in the middle of sort of some Halloween shenanigans over at SETI. So you can see our spooky science pictures or space pictures every couple days. And on Monday, I will be talking to Seth Shostak about how to die on other planets.
Well,
he's the expert, right?
It's Halloween. You got to have a topic that's a little scary. So we're gonna talk about all the different ways you can die on planets in our solar system.
Carolyn,
still working on that book. I just got back from 3 weeks of travel, so I'm catching up on everything.
And where can people find out more?
Oh, let's see. You can find me on Universe Today. You can find me at thespacewriter.com and also at @spacewriter on Twitter.
Wonderful. And of course, I'm Universe Today on all the things. Like I said, I've got an interview with Judy Schmidt coming out tomorrow morning. I did an interview today with Michael Daly, who is this researcher working with bacteria that can survive under the surface of Mars for about 280 million years, which is pretty interesting. On Friday, I'm interviewing Lee Feinberg from JWST, and we're going to spend time to find out, how's it going? How's the telescope doing? What's it been like pointing this wondrous machine at all of these targets? So hopefully we'll give everyone a really good update on everything's going. So stay tuned to my YouTube channel. I got lots of really amazing interviews coming up in the next couple of days. Plus, I got a whole bunch more. I've got an interview about stellar engulfment, psychology of astronauts. So I got lots of really good stuff. All right. Well, thank you everyone for joining us this week. Thank you to all of my co-hosts. Thanks for everyone watching us both on YouTube and on Twitch. Thanks to the moderators. A special thanks, as always, to Nancy Graziano for organizing this whole thing. We do this for you, Nancy. Thanks to Pamela for engineering behind the scenes, even though she is waist deep in mice. And thank you to our special guest. It was so great to talk to Dr. Sheikh. I've been looking forward to that conversation for quite a while. All right, we will see all of you next week. Thanks, everyone.
Bye, Ron.